Welcome back to Physical Science 101. This is the first lesson of Unit 2. The topic of Unit 2 is force. Here's an overview of the topics in Unit 2. First, I'm going to talk to you about forces themselves and some forces that you're going to encounter throughout this course. Next comes specifically unbalanced forces. And unbalanced forces are the subject of Newton's second law. Next, we'll talk about balanced forces, which are the subject of Newton's first law. And then finally, force pairs, which are the subject of Newton's third law. Okay, let's talk about force. You may have learned in high school that a force is a push or a pull. And that's a good enough definition for us. We'll just work with that. Now, force has to be measured, so the SI unit of force is called the Newton. If you're going to write it out, lowercase Newton for Isaac Newton. And if you're going to abbreviate that, it's a capital N. So one capital N is 1 Newton. Now, a Newton can be broken down into kilograms, meters, and seconds, as 1 Newton is 1 kilogram times 1 meter per second squared. So in terms of meters, seconds, and kilograms, 1 Newton is 1 kilogram times a meter divided by a second squared. And that breakdown is going to be important when we start talking about Newton's second law. So the SI unit of force is 1 Newton, which is 1 kilogram times a meter divided by a second squared. Okay, most forces require contact to act. Normally you have to have contact to push or pull on something. However, a few forces, such as gravity, for example, and magnetism, do not require contact to act, but act through what's called a force field. Let's take this marker here, for example. I'm holding this marker up here, but the marker is also being pulled by the Earth. The Earth, through gravity, is pulling down on this marker. The mass of the Earth is pulling on the mass of this marker. So how does that happen? How can the Earth pull down on this marker, which it evidently does? If I let go, the Earth, you can actually see the Earth pulling it down. So when I hold the marker here, I'm pulling up, I'm exerting an upward force while the Earth is exerting a downward force. How does that happen? Well, that happens through the gravitational force field. The Earth, as a mass, creates a gravitational field all around it. So since we are near the Earth, we are in the Earth's gravitational field, and specifically, we're focusing on this pin. This pin is in the Earth's gravitational field. So through that gravitational field, the Earth reaches up and pulls down on that pin. And so that field reaches up and pulls down on that pin. So that is a force field. So gravity acts through a force field. Electricity and magnetism also work through force fields. Now, force fields don't always pull, they can push as well, and we will get into that in later chapters. Okay, so another thing is that Earth pulls specifically down on that pin. The Earth, the force field, is pulling down on that pin, or I can push up on that pin, or I can, if I were to throw the pin sideways, I would be pushing sideways. So the direction of force matters as well. So what does that tell us? That tells us that force is a vector. Not only is the amount of force important, but the direction is important as well. So when we draw force diagrams, we will have to include an arrow to represent each force on an object. Okay, so for when we draw diagrams of forces, we will draw the forces in as the arrows. Now, another thing that will be important is the concept of balanced forces versus unbalanced forces. If all the forces in each direction, meaning sideways or up and down, are the same, then the forces are balanced. Let me go through some examples of that. Okay, here we have an object. So once again, we don't have to get fancy. That's an object. And let's say that we have a force of 5 newtons to the right. Okay, right now, that's the only force on that object. So that force would be unbalanced. There is no other force to balance that. So this would be an unbalanced force situation. Let's add another 5 Newton force to balance that. Now the direction of the other force is important, okay? If I draw 5 newtons to the left, then those forces balance each other. However, if I take those two 5 Newton forces and I put them both to the right, then those would be unbalanced forces. Because they are both pushing or pulling to the right, so they are not balanced. If I have a 5 Newton force to the right and a 5 Newton force to the left, those balance. These two 5 Newton forces do not balance. If I were to have a 5 Newton force to the right and a 10 Newton force to the left, even though there's a force in either direction, they are different amounts. So now I have a force to the right, a force to the left, but different amounts. That's still unbalanced. Those are unbalanced forces. How can I balance that 10 Newton force? Well, if I keep everything the same, 5 newtons and 10 newtons, and I'll add another 5 Newton force, another 5 Newton force to the right, now I do have balance, because these two 5 Newton forces will add up to a 10 Newton force to the right, and that will balance the 10 Newton force to the left. So these are, once again, balanced. Okay, now that's right and left. We can do the same thing up and down. If I have an object and I have a 5 Newton force downwards, such as, for example, the pin in my hand earlier, that could represent the gravitational force pulling down on the pin. Well, I can balance that with 5 newtons upwards. So that would be balanced. But once I let the pin go and all we had was the 5 Newton force down, then that was an unbalanced force situation. And finally, the forces do have to be in opposite directions. So if I were, for example, to have 5 newtons to the right and 5 newtons up, that would still be unbalanced. If I wanted to balance those forces, my force to the right would have to be balanced by a force to the left, and my upward force would have to be balanced by a downward force. So that is the idea of balanced and unbalanced forces. Forces are balanced when the total force to the right is balanced by the total force to the left, and the total force upwards is balanced by the total force downwards. Now, if you have more than one force to the right, you can add those together to balance whatever you have to the left or not. 2 forces to the right would give you an unbalanced force to the right if there's nothing balancing them to the left. Okay, let's talk about some specifics, some specific forces. Okay, let's talk about some specific forces. The first one that I want to talk about is weight. Weight is actually the force of gravity on an object. And we have an equation for weight, which is that the weight of an object is equal to its mass, the object's mass. So weight is the mass of the object times the gravitational field that that object is in. Okay, so in symbols, that would be W for weight equals M for mass times G for gravitational field. The SI unit of mass is a kilogram, and the unit of gravitational field would be newtons of force per kilogram of mass, so that when you multiplied mass times gravitational field, that kilogram would cancel out, so that you would be left with newtons of weight. So weight is a force. Newtons of weight, newtons of force. Weight is the gravitational force. Now, the gravitational field depends on where you are. So for example, on the Earth, the gravitational field is 9.81 newtons of force per kilogram of mass. So the G, the little g, on Earth is 9.81 newtons of force per kilogram of mass. So that means that, for example, 1 kilogram of mass would have a weight of 9.81 newtons. So there's 9.81 newtons of weight for every kilogram of mass. On the moon, things are different. The gravitational field on the moon is only 1.6 newtons of force per kilogram of mass. So if you bring an object from the Earth to the moon, that object's mass will not change. A kilogram of mass will stay a kilogram of mass, but the weight of that object will change because the gravitational field of the moon is weaker. It's about 1/6 of the gravitational field of the Earth. So on the Earth, the gravitational field is 9.81 newtons of weight for every kilogram of mass. On the moon, the gravitational field is only 1.6 newtons of weight per kilogram of mass. So mass doesn't change, but weight does as you encounter different gravitational fields. Let's do a quick calculation of that, because that's something that we're going to be doing a lot of throughout this course. Okay, what I would like you to do is to actually calculate the weight of a 5.2 kilogram object on Earth. So I have to be specific. I have to tell you that this is on the Earth, because if this 5 kilogram object were on the moon, it would be different. So figure out why I had to tell you that it was on the Earth and calculate the weight of a 5.2 kilogram object on Earth. Okay, let's check you. Here is our 5.2 kilogram object. The weight is a downward force. Weight, the direction of weight, the direction of gravitational force basically defines what we mean by downwards. So we know that the gravitational force will be downwards. That's the definition of down. The direction of gravity, the direction of weight, the direction of gravitational force defines down. So we know that the direction of weight is going to be down, so I'll write that as W. So that is our weight force vector. Our weight force vector is down, and we know that we can calculate weight as mass times G. So the weight is mass times g. We know that the weight is 5.2 kilograms. And we know g because I said that we're on the Earth. So since we're on the Earth, we know that weight is 5.2 kilograms times g for the Earth, which is 9.81 newtons of weight per kilogram of mass. So now you can see that I have kilograms in the numerator, kilograms in the denominator. My kilograms cancel out. And the only unit I'm left with is newtons. So weight is some number of newtons. Now I need to multiply those two numbers together. 5.2 times 9.81, and that gives me 51.0 to three significant figures. 51.0. So the weight of a 5.2 kilogram object on Earth is 51.0 newtons downward. We have to say the downward because weight is a vector, so it has both an amount of 51.0 newtons and a direction of downwards because weight defines what downward is. Okay, the next force that I would like to talk about is the force that a rope exerts on an object. So if you pull on an object with a rope, then the direction of that force is going to be in the direction of the rope, and the amount of the force is equal to what we call the tension in the rope. So the tension in the rope tells you the amount of force that the rope exerts, and the direction of the force on the object is in the direction of the rope. Now springs are similar. A spring can also pull on an object with a tension force, or it can also exert a compression force, meaning that a spring can push on an object as well. So the tension is the amount of the force. So tension must also have units of newtons, and the same thing for the compression. The compression would also have units of newtons. The compression force would have units of newtons. So the direction of the force is either in the direction of the rope or in the direction of the spring, or possibly with the spring, the force could be away from the spring. So let me draw a few diagrams to explain that. First, I'm going to draw an object hanging from a rope. So there's my object. That object is hanging from a rope. Well, the rope is pulling on the object in the direction of the rope. So the force from the rope, which I'll draw with an arrow, is in the direction of the rope, and the force is equal to the tension in the rope. So the direction of the force exerted by the rope is in the direction of the rope, and the amount of the force is equal to the tension in the rope. Now let me draw that object hanging from a spring. Same object, but now it's hanging from a spring. Well, in this case, the situation is similar. The spring is pulling on that object, so it's pulling upwards in the direction of the spring. So the force is equal to the tension in the spring. Okay, so the rope is pulling in the direction of the rope. The spring is pulling in the direction of the spring. The force exerted by the rope is the tension in the rope, and the force exerted by the spring is equal to the tension in the spring. However, a spring can not only pull, it can also push. The spring can pull in the direction of the spring, or it can also push away from the spring. So let me draw my object again, but this time it's on top of a spring. It's being supported by a spring. And in this case, the force from the spring is pushing upwards, away from the spring. and the force is equal to the amount of compression in the spring. Okay, so a rope will only pull on an object. A rope will only pull on an object in the direction of the rope. You don't use a rope to push on an object. You can only pull with a rope. So the rope will pull in the direction of the rope. So the direction of the force will be in the direction of the rope, and the amount of the force will be equal to the tension in the rope. Similar for a spring. If a spring is pulling on an object, if a spring is stretched, if a spring is elongated, then it will pull. So as we hang this object from the spring will stretch and elongate, and the spring will pull back on the object in the direction of the spring with a force equal to the tension in the spring. However, if we place an object on top of a spring, then that spring will compress. So if you compress a spring, then it will push away from the spring. So if I put this object on the spring will push back away from the spring with a force equal to the compression in the spring. So ropes only pull in the direction of the spring, the ropes only pull in the direction of the rope. Springs can either push or pull depending on whether you've stretched the spring or compressed the spring. Next, we'll talk about the forces exerted by a surface. So, for example, if I place an object on a surface, then that surface will exert forces on that object. And there are two forces in particular we're going to talk about: the support force and the friction force. The support force is the force that keeps that object from going through the surface. And so the amount of the support force is whatever is needed to keep that object from going through the support force. And the direction of the support force is always perpendicular to the surface. Okay, always perpendicular to the surface. So if the surface is flat and level, then the support force will be up. But if we have a ramp, for example, then the support force will be at an angle. Let me draw you some pictures of that. Okay, so here I have an object on a level surface, a flat level surface. And in that case, the support force will be upwards. But if the object is on a ramp, then the support force will be perpendicular to the ramp. Okay, so the ramp is pushing in this direction. Now, a quick question: does it matter if I draw the arrow up here or down here? No, it doesn't really. What really matters is the direction of the support force. So I could just as easily have drawn these diagrams like this. Okay, if I draw the support force up here or down here, it doesn't really matter because they're both forces upwards. So what really matters is the direction of the force, not exactly where I draw the arrow. So once again, for example, if I draw the support force up and to the left right here, or up and to the left on the bottom of the object, that part doesn't really matter. What really matters is the direction of the force. Okay, so the support force is the force that keeps an object from going through the surface, and that is always perpendicular to the surface. Our other surface force is the friction force. Now, whereas the support force is always perpendicular to a surface, the friction force is always parallel to the surface that an object is on. So the friction force is always parallel to the surface. Now the friction force is very interesting. If an object is not moving, then the friction force can change. The friction force can can be 0 or it can increase to offset, to balance an applied force up to a limit. Once that limit is exceeded, then the object will slide and the friction force will be a constant amount. Let me go to a computer simulation so that I can demonstrate that for you better. The simulation I'm going to show you is something that you can go with and play with yourself. So I'm going to show you how to get to it. To find it, just Google PHET, P-H-E-T, physics. P-H-E-T, PHET, physics. And it popped up. Let me search for that. When I search for that, we have phet.colorado.edu, PHET, free online physics, chemistry, biology, earth science simulations. So here I go to simulations. And PHET itself stands for Physics for Everyday Thinking. And this is a project of the University of Colorado at Boulder. And the particular simulation that I will use is down here, forces and motion, basics. Okay. Now once again, you can go to these yourself and play around and learn from them. I recommend it. It's both fun and educational. Okay, I'm going to click on this one that says friction. And let's see, I'll show the sum of the forces, values, and I'll show the speed. We're not going to deal with that right now, but we'll need it later, so I'm going to pull them all up. So here I have a box. That box is our object. This little mannequin will exert our forces. So I'm going to have the mannequin push to the right with 1 Newton of force. So I have 1 Newton of applied force to the right and 1 Newton of friction force in response to the left. So I've increased it to 2 Newtons. So notice as I increase my applied force, and the little mannequin pushes harder and harder, the friction force increases. Okay, so I'm applying a greater and greater force. As I apply the greater and greater force, the friction force increases. Now I'm applying a force to the right. I could apply a force to the left. Let me release my force. And notice as I release my force, the friction force changes, the friction force decreases, but now that I'm pushing to the left, the friction force is increasing. So the friction force, what we call the static friction force, is increasing in response to my mannequin's force. Okay, I'm going to have him push back to the right, and I'm going to have him push and push and push and push, and push and push and push and push, and I'm going to have him keep pushing until the box starts to slide. Now notice that now I'm applying 142 newtons of force and there's only 94 newtons of friction force, which gives me an unbalanced force to the right. But notice now if I push more or less, the friction force doesn't change. The friction force stays 94 newtons no matter how hard I push. Okay, let me back off. I'm going to make my force 0. So make my force 0. Now, the only force on the box is the friction force, and it stays the same. So when the box is moving, whether I'm pushing or not, the friction force stays the same. And the box is no longer sliding, so the friction force goes back to 0. So now, if I push again, the friction force responds, and that will happen. So the harder I push, the greater the friction force up to a limit. And once I exceed that limit, and the box is sliding, then the friction force will not change anymore. So now the friction force is staying 97 newtons no matter how hard I push or what direction I push in. I can even start pushing to the left now with the friction force, and the friction force will still not change. Okay. So the friction force is 94 newtons no matter how hard I push when the box is sliding. When the box is not sliding, the friction force responds to my force to keep the box from sliding up to a limit. But once that limit's exceeded, the box will slide and the friction force will stay the same no matter whether I'm pushing or not. No matter how hard I push or even whether I'm pushing, the sliding friction force will stay the same. Okay, we're going to come back to this. But for now, we're going to talk about a couple of other forces. Okay, just a couple of other forces to talk about. The first is air resistance. It's like friction, except that air resistance depends on two things. One is how fast you are moving relative to the air, or how fast the air is moving relative to you. If you're standing still and there's a wind blowing, that wind is exerting an air resistance force on you. If you're on your bicycle moving through still air, then that air is exerting an air resistance force. So as long as an object is moving relative to the air, there will be an air resistance force. However, unlike friction, the air resistance force depends on speed. It also depends on the size of the object. So that's why, for example, bicyclists, when they want to reduce their air resistance force, they will scrunch down and make themselves smaller to have a smaller air resistance force. And finally, a person can exert an applied force on an object. So just like my little mannequin exerting a force on the box, the mannequin's force would be called an applied force. Or, as I was holding the pin in the air, we know that Earth is exerting a gravitational force or a weight force on the pin. Well, I'm applying an upward force on the pin. So there are two forces on this pin, weight pulling down and my applied force pulling up. So a person can exert an applied force on an object. And that force can be in whatever direction the person applies the force and whatever amount of force that person chooses to or can apply to the object. Now we're going to talk specifically about unbalanced forces. Unbalanced forces are the subject of Newton's second law. So Isaac Newton's second law of motion. We're going to cover the second law first before Isaac Newton's first law because it's a little bit easier to understand in that way. Now what Isaac Newton's second law says is that when an unbalanced force acts on an object, the object's velocity changes. That is to say that the object accelerates. And Isaac Newton's second law of motion gives us an equation. It says that the acceleration of an object is equal to plus or minus the unbalanced force, the amount of unbalanced force on the object, divided by the object's mass. Or, in symbols, A is equal to plus or minus F over m, where A is the acceleration, F is the unbalanced force, and m is the mass. Now, because acceleration has both amount and direction, and because forces have amount and direction, because they're both vectors, there are two cases to think about. And the first is when the force is in line with the velocity. When the force is in line with the velocity, the object's speed changes. So when the force is in line with the velocity, the object's speed changes, and acceleration is positive if the force is in the same direction as the velocity, and negative otherwise, so if the force is in the opposite direction as the velocity. The other case is when the force is at right angles to the velocity. When the force is at right angles to the velocity, then the direction of the velocity changes. And in this case, the force would be called the centripetal force. And acceleration is always positive in that situation. So if the force is in the direction of the motion or opposite the motion, so in line with the velocity, then the object's speed will change. And the acceleration will be positive if the force is in the same direction as the velocity, negative otherwise. And if the force is at right angles to the velocity, then the direction of the velocity will change and the object will move in a circle. And in that case, we have centripetal force because the force is towards the center of the circle. Let me demonstrate that for you with the simulations again. Okay, here we are with our motion simulation again. There's my box. I'm going to have my mannequin exert a force, and I'm going to have him exert enough force that I have an unbalanced force in the direction of motion. So you can see that my applied force is greater than my friction force. I have an unbalanced force in the direction of motion, so the object is accelerating and it's positive. The speed is increasing. So let me reduce my force. Reduce my force so that we have balanced forces. Okay, now I've made my applied force 94 newtons, which exactly balances the friction force of 94 newtons. So I have balanced forces. I have no unbalanced force, so the object is not accelerating. The object's speed is not changing. I'm going to add some force. So if I have an unbalanced force in the direction of motion, notice that the speed increases when I have an unbalanced force in the direction of motion. Balanced forces, no change in speed. Now I'm going to reduce my applied force so that it's less than the friction force. So now that my applied force is less than the friction force, I have an unbalanced force opposite the direction of motion. The box is moving to the right, the unbalanced force is to the left, and so the box is accelerating with a negative acceleration. The speed is decreasing. So balanced forces, no change in speed. The box is not accelerating. Unbalanced forces, unbalanced forces with the force in the direction of motion, the speed is increasing, the acceleration is positive. Unbalanced forces opposite the motion, so motion to the right, unbalanced force to the left, speed is decreasing. So, and if I just stop pushing altogether, then the friction force is the only force that's an unbalanced force opposite the motion. So, which meant that the speed decreased. So when I have unbalanced forces in the direction of motion, I have a positive acceleration, so motion to the right, force to the right, speed increases. Motion to the right, unbalanced force to the left, speed decreases. Now I can do this in the opposite direction as well. Okay, let me push to the left. Now I have motion to the left, unbalanced force to the left, speed increases. And if I have motion to the left, unbalanced force to the right, speed decreases. So if the unbalanced force is in the direction of the motion, the object will have a positive acceleration and speed will increase. If I have an unbalanced force opposite the motion, the speed will decrease and acceleration will be negative. Okay, let's talk about forces at right angles to the motion. I'm going to go back and I'm going to go to the simulation called gravity. Gravity in orbits. Okay, let me pull that one up. Start that one running. I'll do the model. Okay, so I have the gravity force and the velocity. So here we have the sun and the earth, and notice that the gravity force, the blue line, is at right angles to the velocity. So what will happen is that the Earth's speed will not change, but the direction of its velocity will. And let me start it running and you can see that. Okay, so you see force at right angles to the velocity. The speed doesn't change, but the direction of the velocity does, which means that the Earth moves in a circle around the sun. Now notice that the force is always towards the center of the circle, so that is a centripetal, or a force pushing towards the center of the circle, a centripetal force. So centripetal force means a force pushing towards the center of the circle. So when the force and the velocity are at right angles to each other, that doesn't change the speed, it changes the direction of the velocity, which makes the object move in a circle, which is why the Earth orbits the sun in a circle. Now, if I were to turn gravity off, which I can do in this simulation, then notice that with no force, the velocity doesn't change anymore, and the Earth just keeps moving at constant velocity. So with no force, the object's velocity doesn't change at all. Okay, let's just do one exercise before we leave for this lesson. So here's a question. What is the resulting acceleration when an applied force of 100 newtons is applied to a 5 kilogram object? So I'd like you to apply Newton's second law. So let's see what you can do with that. So pause and then come back and I'll lead you through it. Okay, here I'll draw my object, and the mass of the object, mass, is equal to 5 kilograms, and we have an unbalanced force. I didn't say which direction it was in, so it doesn't really matter. So I will draw my unbalanced force. Let's say I'll draw my unbalanced force in that direction. So force is equal to 100 newtons. So I have a 100 Newton force, which is unbalanced by anything else. So I have a 100 Newton unbalanced force acting on a 5 kilogram mass. I've gotten all my data, I've drawn my diagram. And the question is, what is the acceleration? Well, the principle is Newton's second law, so I can write out acceleration equals the unbalanced force divided by the mass, or in symbols, A is equal to F over M. I have the unbalanced force, I have the mass, so the acceleration is 100 newtons divided by 5 kilograms. So the acceleration, my numbers are 100 divided by 5, and that would be 20. And what are my units? Well, remember that I said that a Newton, I'm going to do my units over here, I have a kilogram. 1 Newton is a kilogram times a meter per second squared. So that is my Newton. My Newton is a kilogram times a meter per second squared, and I'm dividing by a kilogram. Okay, so that's my units. I have a kilogram times a meter per second squared. That's my Newton. and then I'm dividing by a kilogram. Well, my kilograms are going to cancel out, and my units that I'm left with are just going to be meters per second squared. So my acceleration will be 20 meters per second squared, just as we know the units of acceleration have to be. Okay, we're going to wrap it up there for this lesson. We'll come back next time with more exercises. Until then, think science.